here. All right, cool. So we begin the recording. Hopefully this doesn't get in your way on the screen. All right, it's going up. Okay, so today we're gonna cover what we call x86 assembly. Why do I have to specifically say x86? As we said earlier in lecture 9, assembly comes in different flavor. It's a language, right? Oh yes. So we have a Discord session today. So I think we will finish around, to be honest, around 1:30. So afterward, I'm basically gonna go back to my desktop. We'll have a Discord session, if possible. If you don't have time at 4 to 4:30 today, it's office hours. So I'm gonna be on Discord and answer most of your questions. I have to apologize at the time. I have a meeting with my PhD student actually at 4:30. Because we basically are working on one of the paper, so I need to go at 4:30. So 4 and 4:30 will be another Discord session. Any remaining question you can schedule an office hours with me or with Pclip, which is our PhD TA. And I think actually a couple of you already took advantage of that already, and I encourage you to basically take advantage of that. Right? That's our effect of coffee. Okay, so we actually let's move on to x86 assembly. As we said earlier, right? Assembly comes in different flavor, different language. We are going to study x86. Why? This is one of the most common assembly that we see in desktop and server. And this is kind of like the classic assembly that we'll use as you study things like OS and most of the class throughout your undergrad career. Wait, what's the feedback here? Nope, that's not okay. That was from the other year. My bad. So let me basically migrate from the C code to x86 assembly, right? And if you're curious about the feedback, usually I have a feedback right after the midterm. Basically, I would ask you to submit a poll. I basically will gather all the answers and try to improve the class so that I can learn how to make the class better. One thing I do learn is I need to grade the assignment quicker, and we will address it. So hopefully by the end of this week, especially now that we have long weekend, your grade for assignment 1 should be up. And also, your exam should be ready by around Sunday-ish. So if you're not I'm gonna be silent on Monday.
What's the exact time the exam release?
Likely to be around noon. So expect the exam to be released at noon. I have to be honest here, I typically open it like a half an hour earlier to make sure things go smoothly, because if I open it right where the session started, sometimes it doesn't go up on Discord or Canvas, and we have to wait. So I think the best thing to do usually for me is to upload the exam half an hour earlier. So it's around 11:30 you have it. I'm not too worried about you starting early because it's designed to be finished in 2 hours anyway, and you have 30 hours. It's either you know the answer and know how to implement it, or you don't know the answer. All right, from C to assembly, right? So now let's talk about what happened when you run GCC, right? GCC basically translates quote unquote human code. I don't want to say human code in the sense that it's not human language, but it's a C programming language, right? Into computer's own language. Whatever a computer understands, these are in binary. The processor that you buy has its own language, as we discussed in lecture 9, right? So if two processors talk a different language, you need to actually recompile to the two language. And you can actually see an example here where you have to have a compiler for the GPU. Let's say you want to write your own GPU code that runs, say, machine learning or Bitcoin mining or things like that, right? Without relying on TensorFlow or PyTorch, right? You will then need to compile with a specific compiler designed for the GPU. right? It would allow these code to run on a GPU, and the same code cannot be run on a CPU. The CPU would, in this case, would run an x86 assembly. So let's look at an example of x86 assembly code. Here's a code example from C. Simple, right? Any questions about this code? If you have questions about this code, go get coffee. This is basically what's needed to understand this code. Basically, we have a main function. That's the first line where we go in, run the program. The first line is int a equals 0. We assign a to be 0, b to be 5. We return 0 plus 5. That's 5. Right? That's it. If we type in this command, which is called object dump or obj dump, you will see that, okay, no, I need my pen here. So this command with the dash f will deassemble. Will actually assemble the files with your file name .o. That's the result of your GCC. So basically, GCC will create this thing called the object files. The one with the .o. These are executable, basically. These are binary. So this thing essentially is the binary. Computer knows, computer can run. With this binary, you feed it to the command obj dump. Obj dump would give you, okay, based on this binary, these are the assembly code. It provides you the assembly code that you can read and modify. And here's the code, right? So I'm going to move the chat windows a little bit so you can see the code here. Tons of cryptic text, right? Likely to be confusing. But if you look at it, there's a main function here, right? It's a function main, right? What else? You see that there's an address here. We will talk about that in a bit. This side corresponds to the actual binary for each line, right, of the assembly file, assembly code to the right. Basically, 55 translate to push RBP. RBP is a register file. It's a register inside the register files. We will talk about what the heck is that. Basically, when you run obj dump, you are going to get the assembly code, which is to the right. Let me change the color. So these are your assembly code. And to the left is the actual binary. Anyone watched the movie Martian before? Okay, so if you have not, it's a great movie and actually really representative of like the scientific community. Basically, if things, okay, I don't want to swear, but if things turns out really crazy, for example, the COVID pandemic, right? You see scientists working together to kind of like fix some problems, and that movie is pretty like, I love it as a researcher to see the movie that really like represent the scientific community without like the Hollywood flavor, I guess. But one thing, anyone remember the scene where the guy, Matt Damon, like whatever character he's playing, is stuck on Mars and he's basically trying to establish the connection between him and Earth. And he used the hex number to actually communicate. Anyone remember that scene from the movie?
I just remember the potatoes.
You just remember the potato. Awesome.
It's kind of been too long ago.
It is a long movie. But there's a scene where he actually go and try to get this Pathfinder robot. What is a Pathfinder? Pathfinder is this robot probe where NASA sent it a long time ago and it's no one use it anymore because it died, right? But inside there's a computer and it just happened to be at the same exact copy at the lab on Earth. So basically what he did in the movie was, okay, I know there are two pathfinders where they can talk, right? Basically you can establish communication, but you can only just send a camera image, which is not that meaningful if you're stuck on Mars, right? So what he did was, okay, I'm gonna build a hex code so that the camera can point to the actual letter between 0 to F, right? So that you can communicate through ASCII. But that's too slow. So the problem with that movie, with that portion of the movie is the Pathfinder connects through certain communication, and that's more advanced computer. The problem is you don't have the actual channel number, so you can't really modify the communication between the two machines and switch it to another machine. Basically, this is the Earth, right? I'm so sidetracked today. It is Mars. So this is a current communication. What that movie during the time, what the Matt Damon character wants to do is that's another machine which is more advanced, right? And you want to establish this communication which is not possible at the beginning, right? So what the team, basically the hacker from NASA, tell Matt Damon to do is you can go look at this assembly and change a few bytes, basically change these things so that you change the instruction, right? If you change these things, right? You essentially change the instruction here. You rewrite the program so that now you can establish the connection. And also that's why I kind of like the movie, because it's possible to actually do that. It's actually a really scientific way to troubleshoot what will happen if you get stuck on Mars alone and are dying? And hopefully you don't run into that scenario, by the way. But yeah, so when you look at assembly code, these are real. These binary are real. You can modify this. A hacker can come in your computer and modify this too. Basically, if you allow them to write onto the binary file, how chmod 777, right? I can rewrite my own binary files. So these modifying these things allow you to hack the code and change the assembly. And let's break it down a little bit more. Now come back to the class. Now that we talk about the movie, talk about the scene in the movie that's relevant to this class, right? If you look at the code example here, the top part basically is the function name. This is where the function, in this case, the main function is located, right, inside the address space. Skip the virtual part. We'll talk about this toward the end of this module. I have to say virtual address space to make sure this is actually correct. But if you think about it, basically your code is somewhere in DRAM. I always stress this part, right? It's somewhere in DRAM. Over here, it said the location of this code is at 5FA. Any questions so far? That's the address that stores this main function. So that's the first thing I want you to let you know, basically. Any question here so far? Because we're gonna go one by one to make sure it minimize confusion.
Okay, so it's hexadecimal number.
But what?
Is it hex?
It hex, yes. It is hexadecimal. So if you load that address, you're gonna get the main function. That first line of the main function. You see 5FA here, right? That's the first line in the assembly code. The next command is 5FB. The next command 5FE. Why 5FE? The first command is 1 byte, as you can see here, 5, right? It's 1 byte. If it takes 1 byte, so basically here, 5FA, right? 5FB, 5FC, 5FD, 5FE. So the first command say I have the value 55. That's my command, only 1 byte. The next command say, hey, I'm fat. I need 3 blocks here. I have 48, followed by 89, followed by E5. So that's my second instruction, right? This is instruction 1. Instruction 2. What will come next? The next command, which is basically 7 bytes, it's a lot, right? So we see 7, 4, 5, blah, 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 blah. So that's instruction 3. This is literally how your computer store the program in the DRAM. Again, right? Computer is stupid. We need to command everything. And this is basically define how we store this binary on the computer. Any question?
So the second line have 48 on B, 89 on C, E5 on D.
48 on B. Yes, exactly.
Hmm.
Depending on the endianness as well, as we remember the little and big endian, but it's like this: 48 on the first, 48, 89, E5, B, C, and D. And then when it's 5, F, E, next command. If you want to dig a little bit deeper, I hope you look forward to the next class, which cover architecture a little bit, right? So let's go to the next thing I want to point out. The left side, as I said, is the address of each line on your assembly. So 605 basically corresponds to address 605. It corresponds to this move out $0x5 -0x4 or BP. We will talk about what this means in a bit. Right now, I really want you to know the fundamental and what is now stored on your DRAM. You can actually read this number. It translates to the instruction.
So
Okay.
in C, when we have pointers, it actually like one of these addresses have another addresses.
Yeah, you can have function pointer point to the main function, right? Now you can see why function pointer works. You can say, hey, 5FA is my function pointer.
So it's like the move on the assembly.
Oh, you used assembly before, I guess.
No, I'm not sure. I'm just guessing.
Oh, move in assembly means that I'm gonna move the data from here to here. So it's kind of like different a little bit. We will define what these are.
Okay.
Right? Yeah. So we will define what the command are. Over here is the actual bytes that represent your program. Basically, everything here represents that simple program that do int a equal to 0 and b equal 5 and then return a plus b. That's the bytes that represent these 3 lines, right? So these are the actual bits. These are actually what the computer actually sees. So if you have the ability to zoom into your processor and look through the electrons in the wires inside your ALU or the arithmetic logic units, these are the command that they'll see, right? And here on the right side is the actual command. Add EDX EAX basically means I'm gonna take the value EDX, take EAX, add them together and write the result back to EDX. How do you figure out what does the command do? There's a manual for that. Basically, the Intel x86 manual will tell you exactly what does this command do. And if you read it, it will say, I'm gonna take this value, I'm gonna take this value, add them together, and write the result back to this value, this variable. And that's it. So, what else? So these are the actual bits that represent that command. Oh, my bad. It's actually write the result to EAX, not EDX. I forgot. So yeah, as you can tell, these things best consult the manual because it has the description for every single command and you can make mistakes like I did earlier. Right. Okay, so we covered the type of instruction, right? As we said earlier, now I'm gonna kind of classify them based on 3 major types. The first type is compute instruction. This is where you perform like add, multiply, subtract, and or. So these are the actual computation. There's a memory instruction because You need to move data in and out. If you want to add to number, right, this is where your CPU is. Literally, physically, it's like this. Your CPU is here, memory is here, right? And basically over here is your motherboard. Your motherboard connects the CPU to the main memory. If you want to add two things, the address on the CPU, what do you have to do? You bring the data from the main memory to the CPU first, right? That's the first thing you have to do. It's actually located at different places, right? So let's say I want to bake a cake, right? My kitchen has nothing right now. I only have a mixer, right? And an oven, right? So if I want to bake a cake, what do I need? I need a mixer, I need an oven, right? What else do I need to bake a cake? Can someone tell me if I want to bake a cake, what do I need?
Ingredients.
Yeah. Anyone ever bake a cake before? I'm gonna try to come up with one on the fly. And I'm not sure it would become a cake, but I think I know the basic ones, at least the basic ingredients. Obviously, you need cake flour, right? The base for all the cake. Eggs, butter, sugar, and probably whatever flavor you want. So let's say we want to bake a vanilla cake, right? So vanilla flavor, right?
Baking powder.
Baking powder, yes and no, depending on what type of cake you want, actually. If you want to make it more fluffy, I am not expert. I'm just follow instructions, but I did bake a cake a few times before. And some of them would require that. So basically, let's say you gather ingredient. Where can you buy it? Milk? Yeah, that's awesome. Yeah, sometimes you need milk. Depends. You would be surprised how much butter and eggs go into those things that you don't need the liquid. You need to buy it from the store, right? What does it mean? Sorry, I was about to say lazy. Yes, let's just say that. My lazy person would have to walk to the store to get those things, right? It means that if I want to perform this computation, I need to walk from the CPU to the memory to get those data. How do I tell where to get the data? How do I tell where is my data? Address, right? I need the address. I need the address to get my data. So let's say I now got out the data. What do? If I want to bake a cake, I'll mix everything together. I'll melt the butter, put them in a mixer, put in eggs, put in cake flour, and mix them together, and then put in vanilla flavor. So there'll be instructions, right? Instructions. Step 1, do this. Step 2, do this. Step 3, do this. That's your assembly code, right? The instruction on how to bake a cake. Then, based on that, what's the last step? Put everything in the baking thing, the mold, and then put that in an oven, right? 325 to 50 Fahrenheit, 20 something minutes is done. Yeah, you got a cake. Hopefully it's edible. I don't guarantee whether it's edible or not. But at the end of the day, you got a cake, right? And you can eat it. The key here, you need data from the store. That's where you need to load the data. That's the memory instruction. The step 1, step 2, step 3, those are compute instruction, right? What's the last thing? What's the last thing missing that I haven't covered in your program that can exist? I talk about the compute instruction. I talk about the load and store instruction. Load and store, basically, I grab the data. It means I'm loading. I put the data back to the memory. I'm storing the data back to DRAM. What else am I missing? So I can do A plus B. I can do A of 0 equals some value. What else am I missing? Can you program without loop and if else? I'm still here. Why do it's so quiet?
Yeah,
Right now?
sorry, load and store and what again? My internet got cut off.
Oh, compute, load, and store. So we cover these things, right? I can perform addition, multiplication, subtraction. I can perform getting that data from DRAM, putting this data back to DRAM. What am I missing here? If you want to write a program, Am I missing something? Yes, you need instruction for conditional loops, right? I need loops. I need if else. Imagine having to write a program without those things, right? So the last piece of instruction type is control instruction. It control how the program jump from one place to another, right? This determine the next instruction to execute. Most of the time, what do? You go line by line by line, unless you hit this control instruction. Say, if else, if this is true, do this, else do that, right? So now we talk about the opcode, right? The verb and the operand, the subject and object. The opcode is what I highlight here. Push, move, move out, add, pop, return. No op means no operation, right? I kind of I feel I kind of forgot what no op NOPW is actually. So I need to consult the manual. But if you look at this, these are basically the opcode which tell, right, the computer what instruction they're supposed to do. What instruction they're supposed to do. I believe the last no op means that I'm gonna store return 0, which is the condition check after you exit the program. Is it exit correctly or not? So these are the opcode that tells what the process is supposed to do. These are the actual operands, right? What do we push? Push RBP on the stack. Move RSP into RBP. Move RBP -8 into EDX, right? So these percent thing, treat this thing as a variable, right? Variable that you define in C, A, B, C, D. Basically, each of these are keywords that can store value. These are number, right? When you see dollar sign mean an address. Basically, is used as a base address that you want to load into the register called RBP. As I said, register is a variable. It's a temp variable, basically, where you can use. It's already predefined. It's already predefined. There's a limited number that you can use, right? The number that I put in here, the negative 0x8 is actual offset. Like treat that as a number. So treat both of them as a number. The base and the offset. What does the base mean? Basically, it's the base of that value. The offset basically gives you the offset from the base address. And you have the addressing mode, which is how do I interpret this as a value? What does $0x0 minus 0x8 mean? It will be specified in the manual. Basically, if you go to the manual, it will tell you, okay, this is what it means. The operand is the temp variable that's set here at a circle, right? RBP, that's the operand. Basically represent the name of the register, treat it as temporary variable that's involved in the instruction, right? So I talk about register, I talk about this temp variable. What are they? They are extremely fast, tiny unit of memory that is inside the processor, right? Think of it this way. Let's say, again, I want to bake a cake, right? If I buy all those ingredients, where do I store them? I will store them in my kitchen cabinet, right? My kitchen cabinet becomes a register. I'm going to store these things until I no longer need them. And I have limited number of register. These things are visible to programmer. Basically, if you want to write a code in assembly, you can use a register. The compute instruction, add, subtract, multiply, can directly access the value. You don't have to get them from the main memory. So this is already available. A group of register is typically called register files, right? Register files or reg files. This is kind of like architectural term. You will see them in the manual. It said register files, basically, these are all the register you have. What's the difference between register and the main memory? So accessing the data in the register files can be done directly. So these are extremely fast. Typically take one cycle, right? So let's say you buy a 3.4 gigahertz processor. How much time does it take to access a register? How much time does it take? So how much time does it take for one clock cycle in this processor? Let's go back to math. Can someone tell me how much time does it take to access my data from the register? If I have a 3.4 gigahertz processor. Okay, let me go through how to compute that. What's a giga? What does giga represent?
Is it 1,000?
It's 10 to the 9.
Oh, okay.
Kilo is 10 to the
So,
3, mega is
billion?
10 to the 6, giga is 10 to the 9, right? So this is 3.4 multiplied by 10 to the 9 cycle per second, right? This is basically, I can do these many cycle. It means that I can clock these many cycle per second. So
Oh, one hertz is one cycle.
1 hertz, no. Yes, well, no. 1 hertz means that I can do these things once per second. So I can say my processor can clock, right? Basically each time you clock things proceed step by step by step by step. So this is kind of like a digital design concept. Basically this is like a basic computer circuit concepts. If you want to move things over time, you need to clock them. Otherwise you cannot. Basically everything in the digital world is based on a clock. When you clock them, you can proceed to do the next thing. Basically, it allows you to do the next thing. What do I mean? Running the next line on your code, doing the next step of the addition, doing the next step of the multiplication. You need to go clock by clock by clock by clock. If I say I can access a register with just one clock cycle, what does it mean? I can access the register how many times in 1 second? This many times, right? So if I want to access the register once, how much time do I need? 1 over, right? 3.4 multiplied by 10 to the 9, right? This is basically 1 over 3.4 multiplied by 10 to the negative 9 seconds, which is 10 multiplied by 10 to the negative 10, right? Over 3.4 seconds. This is roughly 3-ish, right? This equal to 3 multiplied by 10 to the negative 10, 0.3 nanosecond. To access the register, it only need to spend about 0.3 nanosecond to get that data. For the memory, because it's further away, it's actually taking longer, right? So instead of 0.3 nanosecond, if you read the spec sheet of DRAM nowadays, it's roughly about 10 to 15 nanosecond. So to get one piece of data from DRAM, how many pieces of data I can get from the register? Was 12 over 0.3. 40, right? I can go to the register 40 times. Compare the same time, the same amount of time. If I need to go to the main memory, I can only grab one piece of data, right? So is it clear for the benefits here? Why do you need the register? Because it's a lot faster. Basically, most of the program will get all the data to your processor, and then your processor would do things, right? Again, let's do a baking a cake example, right? let's say your kitchen cabinet and kitchen counter can hold only two things. Or actually two things, too hardcore. Let's say we can only hold four things, right? You have a choice of having eggs, butter, flour, vanilla extract. What else? Sugar, right? So you need five things at least. Five things: sugar, butter, egg, flour, and some flavoring, right? But you can only store four things. What do you do? This is the same situation where your program needs five variables, right? But only have four register. Right? You need five variables and you only have four register. And yes, so you would then grab whatever you can get, right? For the first step, you use all the egg ups. What do you have to do? You need to go back to the store again, right? To buy the last thing. So you have to go to the store twice, right? Twice. The same thing here. You have to go to the memory more times if your register doesn't have enough number of registers to fit what you need to compute. Is it clear now? Actually, yes, you can bring a friend. I'll compare this situation as you have multi-core. You have two processors. Now you have friends, right? I just use this analogy to my surprise, to be honest. You can bring a friend to get two set of items, right? And they'll work together to bake a cake, right? The same thing with computer. You can write a program that use both cores. Together, they make things faster, right? The same scenario apply. So any questions here now that I go like super sidetracked? If not, basically think of it this way: register really limited but really fast. Memory really big, but it's slow, right? How big? Your computer say likely have 4 to 32 gigabyte of memory. How much register do you have? Likely eight items in total. Right? So when you write a program, make sure these things are limited. Make sure you are aware of that. There's a special register called a program counter. Right? This is a special register. The point of having the program counter is basically these point to the current line that you're running. It's as simple as that. The program counter points to the current line that you're running. It's pointed at this. This is my current assembly code I'm running right now. The next cycle will go up, point to the next instruction, the next instruction, the next instruction. The program, as I said, is the data. Program counter, think of it as a pointer that points to the correct line of your program that you're running.
It's like what's called your pawn on a Monopoly game.
Yes. It points to like, this is what you do now. Once you're done, do the next line. Once you're done, it will point to the next line. Once you're done, you point to the next line. It tell the processor, this is the line you want to read. Read this binary so you know what you're supposed to do. Processor said, okay, I've done it. Program counter, proceed to the next line. All right, this is the next line you're supposed to do. Finish this instruction. Processor, okay, fine, I'll do the next line. Program counter will proceed to the next line, and this go on forever until you shut down the computer. Typically, this program counter would increment, right? It go to the next line. Basically, it's as simple as that. You go to the next line. You increment the program counter every cycle. So your program proceeds to the next instruction. This is only the exception of when you have code branch like if else or loop. Why? If true, do the next line. If false, go to there. go to this else statement, right? Which is a totally different location from the next line. Loop, if true, go back and rerun the code on this fraction of the code. So basically, this allows the processor to know where is my current progress. Sometimes in the manual, they'll use the word instruction register or IR. Same concept. It's just a different name for the same thing. Register versus memory versus IO. Think of it this way. You have inputs. Everything in red here is IO. Everything in green is a memory. Everything in blue is inside the processor, right? So you can see the program counter and the register is inside what we call the control unit inside the processor. You have the memory where you can have the address and the data, right? The input will interface. Basically, when you type to the keyboard, as I said, in the interface is the memory. Memory talk to the processor. Processor talk to both the program counter and the register, right? Everything in this dash line means it's a control signal. The control unit send the command saying, read this, read that, do this, do that, do this, do that. Treat it as like a master. Okay, that's a bad example. I shouldn't use master slave. In the company, treat this as like the CEO who tell everyone in the company, do this, do that, do this, do that. All right. So in the Intel x86, how many registers do you have? There are 16 in total. There's a reason why they use this cryptic name. The reason is before this, you only have 8. So you have A, B, C, and D, right? You have A, B, C, and D. As you can see here, A, B, C, and D. These are for the stack, right? These 4 SIL, DIL, SPL, BPL are for like related to code branch, function pointer, and the stack register. So typically we will use A, B, C, and D. A, B, C, and D. At some point, the 64-bit instruction comes into place. Obviously, having just 4 to 8 register is a pain. So they're like, okay, let's have more R8, R9, R10, R to R15, right? So now you have 16 of this register. You have the register that can go just 1 byte. If you say %AL, it's the same as RAX. So this is basically RAX, right? Right. This is byte 0, byte 1, byte 2, byte 3, byte 4, byte 5, byte 6, byte 7. So RAX cover 8 bytes. So let's say you want to load something to RAX, you apply that value to all the 8 bytes. What if you just say, I just want this byte, this 1 byte. This is AL, 1 byte. If you say %AL, it's the same as RAX, but you only take the first byte. If you say AX, you get byte 0 and byte 1. If you say EAX, now you get byte 0 to 3. If you use RAX, you get 0 to 7, right? Historical reason, there's a reason why we call A, B, C, and D. RAX used to be the accumulator. You accumulate, add things up. RBX, base. The B is from the base. Is the base for something. Let's say you want it as the base. Let's start here, and this is the offset. You start from the base. So RBX typically will store whatever you use as the base. Counter, as the name suggests, you count up or count down. RGX is the data. That's why you call it D. SP and BP is the stack and the base pointer. So as I said, this involved with the stack, like management of the stack of your program and the base pointer of the function that you're running. Source and destination index are typically involved with branch command like if else for loop. So these are historical reasons. The way you use this thing, you can use it whatever way you want. Whatever way you want. The name here is cryptic because of the historical reason, right? But make sure you don't use the stack pointer and base pointer because there are some instructions that would modify this automatically. So most of the time, make sure you just use these 4 and these 8. It's a lot safer. All right. So we talk about register. We talk about these are the name of the register. How do I get the data in there? You can use the move command. Basically, move command will move data from one place to another. So you can move from one register to another. Here's the instruction. Move Q means that so you can do move B, move W, move out, and move Q, right? Or just no suffix. Word, byte, quad byte, I think, and this is like 2 bytes if I remember correctly. I might be wrong, by the way. But move Q will move from source to the destination. So the data of the source will move here. The operands that go into the source and destination can be in multiple format. You can have just a number, right? Like this. 10, 0x28. You can move number into the register, put a constant to a register using the $sign. You can use a register, basically put the register name here, it would actually copy the data. You can use a combination of memory plus the register, basically allows these many bytes from the memory, starting from this address given by the register value, and the number of bytes determined by the suffix here, 8 bytes, right? Q is 8 bytes, 1 byte, 4 bytes, at least 2 bytes, I think. And you can have multiple addressing mode based on what you want to store. So this is an example. These are the instruction in the assembly. This is what actually happened in your C code. The stores can be just a number. 4, right? 4, RAX, what does it mean? Temp equal 4. If the destination is a memory, for example, move Q, the destination, when you have a bracket, this parenthesis, it means that treat this as a memory. What does this mean? This is the same as you assign, right? You assign the pointer, use RAX, so this P is the value of RAX. Put -20 to that location in the memory. The location is specified by the value of RAX. Register to register, so this is obvious. Basically, I'm gonna put the data in R9, put it in R10. Basically, if A equal B, you can do register to memory. Basically this, right? As I said, when you see parentheses, it means the location. Treat that value as an address. So this is star A equals B. Memory to register, something like this, right? Now, A equals star B. Take whatever data is at R9 in the memory, put that in R10, right? And you can have addressing modes. This defines how to obtain the operand. For example, you can have the absolute addressing mode like 10, right? The load value this basically means I'm going to load the value address 10 at the address 10 into R0, the value of that address into R0. You have the what we call register indirect. R1 become the address and load address at R1 into R0. You can do a displace of base, which has an offset, right? So this means that I'm going to load the value at offset plus the value of R1. So treat that as an address, whatever this is, give it to R0. So each ISA, as I said, will define how the addressing mode work. So you need to read that. And why do we want addressing mode? Basically, this saves the number of bits required for the address. In a 64-bit machine, your address is 64 bits long, right? Instead of using all the 64 bits for an address, use whatever is stored on the register as the base. Then you use another value to displace that base. Why? This typically is 1, 2, 4, 8, so it's only a few bits of data, right? Otherwise, it requires multiple instructions to process this load command. So here's the x86 addressing mode. So this come back to Intel processor and AMD processor. The format is this. You can have 4 numbers. There's a number in front of the parentheses, what we call constant displacement. There's a number inside the parentheses where I can have 3 numbers: base, index, and scale. This means that I'm gonna get the memory location at D plus the value at base. So this is the base plus D plus the scale, right? Which can be 1, 2, 4, or 8 multiplied by whatever value is here, which is Ri. So that's your address. Start from the base, add D, and then multiply by Ri. So let's say I want to load at 10. Everything here is decimal. Let's just assume these are decimal number. Eraser. And let's say EAX is 10, EBX is 3. My address that I'm loading is what? I'll do one example, right? This will equal, as I said, I'm gonna take, this is D. So I'm gonna take 10 plus, what's my base? What's the base here? The base, again, is the first number. What's my first number? 10, yes. I will then add the result of multiplying this second and the third number. So this is basically what multiplied by what?
3 times 4.
3 times 4, right? So my address is 32. What if I do this? 12, again, EAX. And now EAX is 1000. EBX is 10. So what's the address here?
Plus.
So it's 12 plus something for sure. So what do I add with what?
12 plus 1000
Yes, 12 plus 1000 plus what?
plus 10 times 2.
Yes, so 12 plus 1000 plus 20, that's 1032. Okay. So that's my address. So given this, I can also just do something like this. 12, nothing, 4 and 2. What is that address? 12 plus 0 plus 8, right? So I can not give the number, I can leave it out, right? Any question here? All right, so let's move on. You can do a swap, for example. I want to swap A and B, something like this, right? I have X and Y as my input, swap them together. I would assume, right, X and Y is in RDI and RSI. and assume temp1 and temp2 is in Rx and Rdx. How do I write this in assembly? A bunch of move, right? Oh, sorry. So these basically means what? What's RQI? What's RQI? RDI. What's RDI? RDI is X, right? So this is star X equal what? What's Rx? Temp1, right? This is star. Is temp1 equal star X? Temp2 equals star Y. Right? This is source. This is destination. This means that now star X equal temp2 and star Y equal temp1. Swap. That's it. Any question here? Okay, so
What was the star again?
oh, this is the C code. So the
okay.
pointer, treat X as an address. Just because the input here is star X and star Y, right? So X and Y store the address. You want to store the value at that address. So the corresponding assembly is this 4 line. The first line is I'm gonna take whatever value X is pointing, put that in temp1. Take whatever value Y is pointing, put that in temp2. Then, now that I have temp1 and temp2, I will just then assign the temp2 back to X, temp1 back to Y. All right? Okay, so you can have also instruction to just compute the address, right? Sometimes you want to store the address in a register. Basically, this deal with pointers. Right? If you have pointer in C, it might use this instruction quite a bit actually. So you can use the function called LEA. LEAQ is 8 bytes of 8 bits, 8 bytes of data, right? Source destination. You can use this to deal with pointer and memory references. Also, if you compile the code, sometimes if you have expression of this format, it can use the LEAQ to compute it. Why? This is the scale. This is the index. And this is the base, right? So compiler sometimes use this instruction because it's faster to do x plus k multiplied by y. Here's an example, right? So I want to multiply x by 12. Want to multiply x by 12. I want to use this trick. The assembly code will be, I will use what? This is x, right? This is x. This is the result. This is x multiplied by 12. Or not. It's something, right? So what does it mean? Shift left. So FALQ is shift left. Right? So what's the result of the first line? I have x plus x multiplied by 2. What is this? What's x plus x multiplied by 2? 3x, right? This is 3x. What is 3x shift left by 2? This is 3x multiplied by what? 4, right? This is 12x. So this is one example where you can do assembly tricks to make your program faster. And these are the common arithmetic operation: add, subtract, multiply, shift left, shift right. Logical shift, HHR is a logical shift. XOR and or increment, decrement, negate, not. I'm gonna post. Well, I already post a slide, so you can use this as a cheat sheet essentially on how to write your assembly files. There's also a thing called processor state, right? Processor state are things that you can program. Visible to programmer. Programmer can see, programmer can program. Things like the value in the register, the value in the stack, these are visible to the programmer. the location of the current instruction pointer or RIP, instruction pointer, not rest in peace, by the way, that's where your code is. The current line is running that line of code. You can also have a status of the recent instruction where you compare, like, is it complete? When you compare two numbers, is it result in 0? Is it result in overflow? So here's the condition code. CF stands for carry flag. It's set to 1. If you add two numbers and it results in the carry, what's the carry when you add two numbers? Can someone tell me what's the carry in when you add two numbers together, A plus B? This is kind of like elementary school math.
It's like the digit that is carried from one column.
Yeah,
to
it's like a
another.
digit that you carry over from the previous all digits that you have in the two numbers, right? So if that happened, this was set to 1. 0 would happen if the instruction result in 0. This can be called compare or subtract. Sign means that if you run the instruction and return negative, sign flag would be 1. Overflow flag would be 1 if you do something with two numbers and it overflow into the bits that you cannot store. Let's say you only have 32 bits, your result needs 34 bits, then overflow flag would be 1. So all these flags are set by the instruction. This is done automatically. Why? This actually is really useful for if, else, and for loop, except for the LEAQ instruction that has to deal with the address. So here is the command that you will use and see a lot, compare. Right? Condition code, as it is set implicitly, you can use the command compare to explicitly set these flags. Compare A and B means that I'm gonna basically subtract the two numbers together and set the flag. CF is set if the most significant bit has a carry out. 0 flag is set if source 1 is equal to source 2. As a sign flag is set if source 1 is less than source 2. Overflow flag is set whenever there's overflow. So these are the conditions that overflow happen. It depends on whether the number is negative or positive right now. And this is it's long, so you can kind of decrypt it. But essentially, these mean that you have overflow, the number of overflow into the maximum or the minimum. You can use the test instruction as well. Test Q source 1 and source 2. This is the same as computing source 1 and operation and source 2 without actually writing the results to source 1. Basically, just like compare, but instead of equal, which is a subtract, this is and, like the logical and. And here is the condition code where you can use a set command, set at destination, you set the condition code to a register. You can basically set set equal, set not equal, set sign, set non-sign, set greater than, set greater than or equal to, set less than equal to, set above, and set below. So the condition will be based on what I list here. Again, this is more like a cheat sheet. If you see the set command, this is basically what it means. Note about set X, here's some example. It only set the lowest byte of my destination. So let's say this is my RAX, right? Again, it has 8 bytes. 1, 2, 3, 4, 5, 6, 7, 8. The set command will only set this byte. Yay! So everything else will not be set. Everything else will remain the same. This is a quick recap. So you want to either zero them out or just take that byte, right? So just a quick note about the set command. More on the instruction pointer, basically just point to the next instruction that follow after the current instruction. It's used to alter the flow of the instruction. It gives you the next line of code or go somewhere else, right? It's useful to implement if, else, or for loop. And it can be modified using a control instruction. This is the control instruction. Jump. What does jump do? You move from one place to another, right? It's not the next line anymore. You jump to a specific part of the program. And you can use condition. Only jump. Well, the first one is always true, right? If you see JMP, you always go there. JE, jump only if it's equal. If the zero flag is set, jump not equal, jump sign, jump unsigned, not sign, which is a positive number. Jump greater than or equal, jump less than or equal, jump above, jump below. This is the same as the go to command in C. Basically, this is the jump command. It can be used to implement the loop. It can be used to implement if else, right? So you can use the conditional move, which is C move here. That condition move is the same as the move command, but it only moves if this is true, if that part is true. This is what we call predicated execution. Basically, we run that line of assembly only if the condition code is true. Why? You see this. If x is greater than y, do x minus y. If y is greater than x, you do y minus x, y. This is the absolute difference. You have x and y. You want to see the difference between x and y, but it's the absolute value. You can do it like this. This allow you to replace this if else, right? This if else. You don't have a jump here. No jump command here, which is good. Jump can slow down your processor. Without jump, it allows the compiler to optimize the code even more. So you replace branches like if else with a straight line code with conditional move. And as I said, the benefit is making faster, right? Not much to understand from this slide. This is more beneficial if you want to go to architecture, but this actually make a lot of opportunity for you to optimize your code. This is used, it's used everywhere, and one of the main player that use this is the GPU. Right? This is used in the GPU as well. And don't use conditional move, right? The conditional move, don't use it if the if else is big. Only use it if else is like one line, right? Otherwise, you do twice the work. Both code size on the both if and else has to be saved. We'll actually talk. Oh, a safe code is code that doesn't crash the program. So make sure the conditional move is saved on both sides, and it should have no side effects. All right. We're not going to discuss side effects. We kind of will discuss side effects in OPL, the programming language, and the parallel programming class. I think this is not for you to currently understand. I'm going to brought it up quickly, and you're like, hey, that's a word called side effects. But this will be not be on exam, I assure you. It's a little bit too advanced. All right, that's it for today. As I said, I promised we would leave around 1:30, and we actually got at 1:30. It's a lot of example right now. We will do a recap. We will do a recap once we are back after the midterm. This is a lot of material. The way we'll do a recap is there'll be an in-class exercise that asks you to go through assembly code and tell me what it does. Right now, let's do a recap for the part that might be on your exam. Basically, we ask you to do a parity check and use only logical operation. This is in class 8. This is the last slide today. Yeah, this is the last slide today. I'm gonna basically leave the slide up like this and switch over to Discord, but give me about 5 minutes so I can walk upstairs and use my desktop. Is that okay?
Yeah.
All right, cool. So I will leave the slides up on WebEx. I'll actually turn off
You turn off your